This is the first session for the course Strength of Materials, which is being taken by Professor K. Ramesh. I hope I am audible to everyone. Can someone just let me know?
Good evening, sir. Yes, it is audible.
Oh, thank you.
Thank you, sir.
Uh, this will be the first doubt discussion session for the course by Professor K. Ramesh, and it is on strength of materials. I am Abhinav Chandrakar. I will be the TA for the course along with the second TA, who is Archita Gogoi. So you'll be having two doubt solving sessions every week for this course. The first one will be the one on Friday, which is from 6 to 8 p.m. and it will be taken by me. And the second one will be tomorrow, every Saturday. I think timing you can check. Uh, Maybe you'll be getting mails for this, so you can check there. It must be after in the afternoon, and it will be taken by Archita. Uh, Also, I and Archita have made some initial plans for how we'll be conducting these doubt solving sessions so that it is as effective for you as much as possible. So, we both will initially be summarizing the content that has been taught every week, because I think every week professor teaches around 5 at least 5 to 6 hours of lecture content. So we'll briefly summarize all the core concepts that are being taught for every week, and after that we'll look at some uh, problems which you can solve. And also Archita will be covering the assignment questions which are for that particular week. So all those who have some doubts in the assignment question, they can join tomorrow's doubt session, which will be taken by Archita, and there she'll resolve all your doubts. Today I'll just be summarizing the content and I'll be discussing some questions related to what was taught in this week. If any of you want to say anything or have want to know more about these problem solving sessions or have feedback for it, you can just unmute yourself and let me know. Also, you can feel free to let me know what you expect from these sessions so that we also can prepare accordingly. Since this is the first session, uh, we also are looking to understand how we can do this thing better. So I think Krishna Kant has raised his hand. You can unmute and speak, Krishna Kant. I can't hear you right now. Sure, your voice is very low actually. You are asking if you can ask doubts during the session. Yes, you can. Actually, the reason these two sessions have been kept by NPTEL is so that you can informally discuss about the problems you might be facing, or if you need some help on some questions or some concepts. So feel free to just speak up whenever you have some doubts or you want to ask something. This is supposed to be an informal session, so as much interaction as is possible, it will be good for all. I think I'll first go through the contents of this week and related to whichever concept you have a doubt, there then and there we can discuss it, and then we'll do some problems there also you can ask it. So let me first just go through the concepts taught for the first week. I hope that's fine. Uh, okay, let us start. That was the plan for this session. It will be a 2 hour session, so I'll try to keep discussions related to all the week's content in the first 1 hour. 1 hour. Then we can have a 5 minute or 10 minute break, and then we can continue with solving some questions which are related to the week's content. So this is the transcript which is based on the recorded videos. I'll just briefly go through them. Also, I'll let you know that you will be getting a link for the shared folder in which I'll keep all my resources. So there I'll be having some notes. I'll quickly show it to you. These are some shorthand notes I had made, which highlight all the important concepts that you should be knowing. So these might be useful or might not be useful for you. These are very shorthand notes. And also in the shared folder, I'll be keeping some slides having questions and answers, which I'll be discussing in the sessions, of course. But those who want to look at it beforehand or afterwards, they want to again get back to it, they can quickly take a look and try to solve some of these questions. So these will be in the shared folder and the link will be shared to you by the NPTEL team by mail. So let's quickly go through the content taught in this week. So in the first two lectures, uh, Ramesh sir discussed on introduction to strength of material, where he tried to give you a historical background of how some of the discoveries were made when it comes to understanding the stress that is experienced by materials when they are loaded. And also he tried to show how the understanding of how the stress develops and how we can mathematically represent that, how that understanding was developed over the centuries by the help of numerous scientists. So in that sense, sir has very well brought out and given a good, as well he has discussed very well what are the applications of learning this topic and how this particular topic came up in order to understand how materials work so that you don't have as many failures when it comes to applications such as in structural materials like bridges or some other applications which involve extreme environments. For example, planes which are moving at high speeds, which experience fatigue in many components, repeated loading over number of cycles. So due to these problems, these concepts came up, and also scientists have been trying to understand from an intellectual point of view how stresses develop in materials and how materials deform due to stresses. So both of these tied together, the application point of view as well as the intellectual understanding from an academic point of view. For me also, the historical background of it was quite new, and I felt that that sir has very well brought it out, and it acts as a, if you have gone through his lectures in which he has discussed at length what was the historical background for it, you will get a very good motivation for why this course is useful and how the concepts that you're seeing in the course have been developed over the centuries in a sequential manner. So many of you must have done engineering mechanics related courses before. Maybe for you, some of you it might be new, but few of you who are from a mechanical background or from fields which are related to mechanical engineering, you might be you might have worked with statical mechanics, and there you might have assumed the bodies to be rigid when you are trying to resolve the forces in that body that are being experienced by that body. by making free body diagrams. But for this course, we'll not be considering the materials as being rigid, but we'll make certain idealization in order to understand and have a better understanding of the deformation taking place in the material and the stresses being experienced. So, sir explained about how the uh, stress which is experienced by a cantilever or a beam when it is loaded was discovered over the years. So it will have both a bending stress, bending moment as well as shear stress, and because of that, understanding the stress state in the material in this beam when it is loaded from one end. For example, in in this case here, where you have a simple cantilever being loaded, the stress state in this will not be so trivial since you have both shear and bending taking place, and it will have uh, a triangular shape of loading. So you can call it the stress will be having a triangular form. Maybe there will be a picture showing that. Also, Professor Ramesh has been working extensively on photoelasticity since at least 1 to 2 decades, 2 decades or more. And he has tried to club photoelasticity with the simulations which you can get by using finite element methods. So from these modeling efforts only, it is possible to visualize what will be the development of stresses in a material when it is being loaded in a certain way. But if you want to see it experimentally, there is no way other than using this kind of arrangement where you have a photoelastic material, a polymer, which will show fringes when it is loaded. And these fringes will be telling you what regions of the material have a particular stress. So you can see them as you can understand them as being contours having same stress values. So in case of this bolt, where you have this photoelastic material which makes up this small bolt and this spanner, we see that there are lots of fringes that are present. I hope you have been able to get some understanding of why we are using photoelastic materials and how we can understand what these fringes represent and how these fringes are useful for understanding the stress values which are present in the material. So in brief, I'll say that all these fringes, these represent contours having different stress values. So for example, in this case where you are using a spanner to rotate a bolt, the highest stress values will be near the points of contact, and you can see that as very concentrated colors. And as you move away, you can see these fringes. So all these fringes refer to some stress values. And as you go away from the point of contact, the stress values decrease. Without using photoelastic materials, there is no way to experimentally know how the stress is varying within the material. And that is precisely the reason why scientists have been always baffled, since centuries they have been baffled with how you can understand what is the stress being experienced inside the material. For example, in the case of the cantilever. But by using this particular feature, which is present in nature of photoelastic polymers, it is now possible to visualize it and compare our simulation results with these experiments in order to validate our simulation. In case you have any doubt with understanding what all I have just discussed, please feel free to ask questions, or if you have any inputs you would like to give, you can also give.
Hi, Abhinav. Am I audible?
Hi, yeah, you're audible.
So, just I had a very simple question. The fringes or the suppose the stress values for the photoelasticity.
Yeah.
How do we get how do we exactly get those fringes? Means the range of the fringes. Can you explain a bit on that?
Yeah. How do so? I think your question is, if you have these fringes, from
Yeah,
this, how you can understand what how the stress values are in that material, right? Like for each
yeah,
fringe, what stress values it corresponds to.
correct.
Okay, I see. I think in one of the later slides, it has been mentioned. So from my understanding of it, for example, if you here have this kind of thing, so later you will see that Ramesh sir has actually made some software which can convert your FEM results if you are exposed to FEA, finite element analysis. So there will be some
Yes,
slide
sir.
ahead which will be showing the comparison of FEA results and the ones, yeah, it's this one.
Yeah, yeah,
So this is usually what you will get when you are doing modeling, where you use certain equations in order to mathematically know what are the stress values over a range of time when you're loading a material. So for example, in this case, you get these kinds of contours of the stress, and from the colors you can tell that the maximum stresses will be colored in a reddish color, while the dark blue ones correspond to 0, 1. So
yeah,
Professor Ramesh has developed a software in IIT Madras where which can convert these different. So these might not exactly be the stress values. This might be in particular direction, but he has converted this to a more representative stress value, which can be compared to the experimental photoelastic fringes which you see in the photoelastic material. So now
yeah.
you can compare this, and this will give you, I think, a average stress value which is being experienced at any particular point in the material, and you can compare this numerical result with the experimental one. And here also, just like you had a gradient from 0 to 20 megapascal for the FEA one, you can also develop a similar scale for being able to understand what the particular color of the fringe is telling you about the stress value. So
Yeah,
here you can see that there is a similar scale,
yeah. The
and
contours
using,
are what I see is so for the FEA one, the contours are very visible and they are in the software itself.
yeah,
But
yes.
for the photoelastic, this do we have the fringes or the range of this stress value? So we see right from blue to red for the FEA one, and similarly we have
Mhm.
for the photoelastic one also.
Yes.
So those range are they readily available during the experiment, or do we have to develop it after the visualization of photoelastic contours?
Mm, yeah, I get your question that if you are seeing this kind of fringe, then is it possible to convert this to stress values readily, right?
Yeah,
Hmm. So I am not very sure because I have not personally used this by myself. I came to know about this through this course only, but I think there might be some ways to convert this particular image into uh, a stress value for every pixel that you can see on this image. So here you have a scale, but how they do it in for their own experimental purposes, that I'm not sure. I'll have to check once.
so tomorrow I think again we have a session, right?
Yeah.
You will be only taking the session.
Archita will be taking, but maybe we can try addressing. We can give some more information related to the photoelastic part of the. So we can give some more information related to how they do the analysis of this photoelastic material results that they get. So there maybe I'll talk to Archita and we can explain it there tomorrow.
All right. So one more question. Are you personally connected with Professor Ramesh?
I am, yeah, once in a while we take some inputs from him for conducting these sessions. So I am in touch with him.
All right, all right. Because I am going through a book, Theory of Elasticity, by Sadhu Singh. I guess I have started means just started the book. So it is all about strain gauges and photoelastic only. But I have
Oh,
just
I see.
gone through the book. I did not go. Actually, I have not started reading the book. I just
I
saw it
see.
there. So I'll read it
Okay.
tomorrow. I'll read it.
Okay.
I really
We,
wanted to know more about this because through this video lecture only, I was actually introduced to photoelastic contours. Before that, I had no clue of photoelastic.
yes, I see. Okay, you are Omkar. So we'll
Yeah,
also try to uh, understand this better from our end, and we can maybe keep a small session tomorrow itself where we can discuss in more detail how this, what are the steps involved in this process, and how we can use this particular uh, tool of using photoelastic material.
sure. Even I'll go through the book for the photoelastic thing.
Okay,
Thank you, sir.
thank you for asking. Are there any other questions?
I think Debashis wants to ask.
Yeah, you can ask for that.
Uh, sir, actually, Omkar sir is very interested about the photoelasticity. So there is another parallel course is going on by Professor K. Ramesh only. The experimental stress analysis. Sir, you can explore that also. That is all about this photoelasticity.
Okay.
Okay. Thank you so much for bringing to my notice. Is it a NPTEL course only?
Yes,
Swayam
sir. It
course?
is a NPTEL course. It is a NPTEL course. Now it is going on only experimental stress analysis.
Okay, I'll just write it down and I'll check it. Mental stress.
Thank you, sir.
I
Thank you.
thank you, sir.
Also, you have, I think there are there is a chat option available. So you can put any useful links you get to resources here in chat and everyone can get access. Okay, so we discussed about fringes. And now coming to what are some assumptions that we'll be making before we move on further to other topics in this course. So it was discussed that when you are approaching any engineering problem, usually the real world problems are quite complex. There are lots of different factors and lots of nuances even within this simple problem. So in order to tackle them effectively and using a mathematical approach, it is very important to simplify it to a large extent so that it is possible to mathematically represent the problem and then start solving it. So for this course, we'll be making certain idealizations. And there will be four assumptions that we'll be making. So first will be that we'll be working with small deformation only. And what this means is that we'll not look at the, so every material when it's loaded to certain extent, it will start to deform plastically. And that what that means is that the deformation will not be reversible, but we'll not go to that extent. We'll only consider small deformation which means that the material can always come back to the material is in the elastic regime and it can come back to its original position once the load is removed. Secondly, the material is homogeneous, so it has the same property at every point. The material is isotropic along any direction. If you try to measure the property, it will come out to be the same. Unlike many actual materials like wood, which sir will explain later on, is orthotropic. Also, we assume the material to not have any defects. It can be considered as being a elastic continuum. So these are some assumptions we'll have to make in order to, um, since we are taking the first steps into understanding strength of materials, in order to mathematically represent many of the concepts, we'll always be assuming all of these. So, sir has talked about how the investigation of the stress state in a loaded beam uh, was evolved over the centuries. I'll skip that part because it will take, sir has explained it in a much better fashion. So I won't go through all of that. I think we can directly go to, I'll quickly go through all of these initial concepts so that we can spend more time on understanding stress tensor and related concepts. So important thing related to brittle and ductile materials is that depending on how the material is, when you load it, the failure that you will observe or the nature of the failure you will observe will be very different. In case of brittle material, you are more likely to have a kind of failure which is perpendicular to your loading direction, and it usually can be seen as forming a very sharp cleavage edge at the point of failure. While in ductile materials, you will more likely see a cup and cone feature, which we'll also see in the next slide, which is at about 45-degree from the edge of the material, from the surface. And why that happens, we'll also understand that over the subsequent lectures. Here also a picture of that has been shown, a cup and cone fracture for ductile material. Uh, Sir has told about how by using fiber reinforced composites or FGM, so these are not isotropic materials, these are not homogeneous, but using them can help you to get much improved properties in your real life scenario. And Sir's work has been majorly on on using photoelasticity for comparing it to FP analysis, and he uses additive manufacturing to develop those photoelastic materials. This I had already explained. Now we'll try to start with some basics of mechanics, which will act as a foundation for the rest of the lecture. Yeah, so please go ahead.
Professor said that when we climb the stairs, our bone is subjected to compression and torsion. Compression is okay, I guess. Our femur bone will come subjected to compression, but where the torsion is created.
Okay, compression and torsion. You are Bhuvani. Bhuvanesh, can you repeat like what kind of loading you are giving? I didn't get.
Sir, when we climbing up the stairs,
Okay. Yeah.
Professor said that our bone is subjected to compression and torsion.
Okay.
I guess our femur bone will subjected to compression.
Hmm.
Torsion is created.
Okay. How is torsion created? Right? When you are trying to climb stairs.
Yes, sir.
I see.
Yes, sir.
So we can maybe try to think about it. What might be happening? I have not. I think I missed that part of his lecture. But let's say you have a. Let's just try to understand physically. If you are trying to climb a stair, maybe here you have. This is your leg. So of course your body weight is there on you. So if you make a video of your leg, that is experiencing compressive load. But also, let's say uh, you have to move to the next stair. So for that, you'll have to uh, push onto your heels. If this is your heels, in such a way that your body moves forward, right? So um, so when you're doing that, I think it depends on what part of your climbing you are seeing, because one portion is trying to move one leg on the next stair, and then the other portion is, so in that first portion where your other leg is moving to upper stair, there will be some uh, pressure that will be exerted on your leg, so it will be experiencing some loading. And when this leg will be going to the next step, the second leg is already in the next step. When this one will be going to next step, there will be certain loading. But let's assume that, let's quickly look at it. So you have this kind of a stair. You have one leg on this stair, and your second leg is also here, but this will be moving to the next step. The next step. So what is happening is your first leg is stationary, the leg we are looking at, whose forces we'll try to understand. So this leg is stationary, but the other leg is moving, and that for that movement, some loading will be experienced by the stationary leg. So when you are moving it, essentially you are trying to uh, put a force on your stationary leg in such a way that the your body can swing forward and move to the next step. And for this to happen, there will have to be some kind of a movement that your body will have to experience, right? So let's say this is your leg. Then if this is your body and it is trying to move forward in a way so that your other step can move to the next step, so along with this compressive load, which is there due to your body weight only, and also because you are trying to move to a higher height, there will also have to be a movement which will help you to move that body forward. It will provide a force which will then subsequently get your body to go forward. Some acceleration will be given to your body, and that's why I think there will be this kind of a movement. So you mentioned that there will be a torsion also, right?
Yes,
But I am not sure why torsion should be there. Maybe I'll go
okay,
through
sir.
the lecture or think about it more, and tomorrow we can just again come back to this for few minutes.
Okay, sir, sure.
Okay. Thanks, Bhuvnesh, for asking. So we were here. Any material, if we are considering small deformations, we can assume it to be a spring for simplicity. And we know that when we have springs which are elastic, then we can write the uh, relationship between the force and the extension of the spring using this kind of equation. Considering that the effect of extension is linear on the force, and also if the springs are in parallel, then their elongations will be the same. So this will be the condition, and the effective k value or the stiffness will then become k1 plus k2. While if it is in series, it will become, in this case, the load being experienced will be the same for the two springs. So k effective will have this kind of expression. If any of you have doubts in these, you can let me know, or else I'll keep on continuing. And using these two different expressions, you can write the effective stiffness for any arrangement of these springs.
Sir, I have one doubt in the session. Can I ask one?
Okay. Yeah, yeah.
Sir, during the lecture time, sir has said the stress line diagram for the three different cross sections will be uniform. So I have one doubt. The cross section with a more neck region will fail first. Am I right, sir?
The stresses for all three cross sections will be uniform.
Yes, the stress strain diagram for all the
Hmm.
three varying cross sections will be uniform.
Okay.
But so what I'm saying is, the cross section with more neck region will fail first, and accordingly, the next failure will happen. So the fracture limit will change from different cross section.
Sir,
Okay.
are you there?
Then how the stress strain diagram will be uniform for that three different cross sections? I have this doubt.
Okay. I see. Uh, Krishnakant, you also have some questions? Is it related to what Bhuvnesh asked? If it is, you can also ask it.
Am I audible?
Yeah, yeah, you're audible.
Hello?
Yeah, you're audible. Uh, Krishnakant, you have something, you can speak up if you want to. I think Santosh also has raised his hand. So the question which was asked was, if you have different cross-section area, will the stress strain diagram change or remain the same when you are loading it till fracture, right? Bhuvnesh, that was your question, right?
Yes, sir.
That if you have different cross-section area, how will it affect the stress strain curve?
Yes, sir.
Mhm. So if you, for example, let's just consider this particular case. We know that if this is a mild steel specimen or some similar metallic alloy, it will have this kind of a curve. We'll have an initial linear region, then we might have this kind of region due to some material specific properties, and then we'll have a plastic region until the ultimate tensile strength. But here, what we are plotting is stress versus strain. So this stress is nothing but the force divided by the area, and strain is nothing but the elongation divided by the initial length, right?
Yes, sir.
So just from this expression that we're using, force by area, you can understand that we are trying to normalize with respect to the force.
Yes.
So if the cross section is increasing, the force that is required to cause an extension will also increase, so that the same stress is being experienced by the material. And so it is expected, and we do know that if you have a material which is of different cross section, the force experience will be different, but still the stress value that is experienced will remain will remain the same for a particular extension to happen. So you will see the same curve, but the thing that will uh, happen after your failure is that once your failure starts, which will be this point, ultimate tensile strength. So after that, you have very localized deformation taking place. The highest stress is being experienced by a very small region in your specimen. So when this happens, the geometry of your localized region has a very important role to play on how much will be the stress required to cause further deformation. So you'll see that as you change the cross section area, there will be some change in the curve post the necking region. So in this region, there might be some change. You might see that for particular material, the deformation or the ductility is much more after your necking region, while for certain cross sections it is lesser. But that is not of concern to us for this course, because we are only looking at the elastic region, small deformation. So you can consider that the stress strain curve will be the same irrespective of what is the cross section area. I
Sir,
hope. Yeah.
another one
Santosh,
question. Hello, sir. Am I audible, sir?
yes, you're on.
Sir. So I'm having that three specimens: specimen one, specimen two, and specimen three. Okay, I am
Yeah,
loading that three specimen in the UTS machine. Okay, universal testing machine, and I am doing this strain test. Okay,
yeah.
so does the yield point and ultimate point for that those three specimens will be equal, sir?
Yes. If you have three specimens of the same, made of the same material
Made up of the same
with
material. I
just
am doing
different geometry,
a
like
different
not
geometry.
different dimensions, you mean.
Uh,
So as I just explained right now, uh, since you are looking at the stress versus strain curve and not
yes,
the force versus extension curve,
yes,
so your yield strength and ultimate tensile strength should not change at all if the material is the same. But of course, if there are some defects due to some statistical reasons, due to some variations, there will be some small change, but the dimensions will not have an effect on the yield strength as well as the UTS.
And have you did this test as a practical, sir? Have you performed this test as a practical?
Yeah, we have performed it.
Okay, thank you, sir.
Mhm. You can also see this test in any mechanical related lab.
Okay. Previous days I searched in internet, but what I get is the stress strain curve was different for various cross sections like that I get from the internet. So that's why I am asking. But concept wise, it should not vary. It should be same for uh,
Yeah.
various cross sections.
Mhm. So maybe you can, if you still have doubts, you can share with me the link to the whatever resource you use to look up about this, and I can maybe help you with it. But in general, they're due to different variations in the defects in the material
Okay.
or some changes between two different specimens.
Okay.
Always it is not totally homogeneous. There will be some small differences. So if you have this kind of a curve, if
Okay.
you plot for multiple specimens, it might be something like this. Usually the
Okay.
ductility percentage changes a little, but the strength is almost the same.
Okay.
So
Okay.
even for experimental purposes, we never use just one single specimen. We use at least three different specimens of the same material to get
Okay.
some representative results. So if this is clear, we will proceed, or if there are any other questions related to this, you can ask.
Oh, no, sir.
So I think this is a good plan that we can firstly just go through the content, and those questions which I am not able to address in this session, they will be addressed in the next session.
Okay, sir.
Okay, sir.
Okay. So after looking at the deformation in materials, the elastic deformation, we'll also look at uh, how the deformation will be for a ring which is experiencing uniform hoop stress. So for example, if you have this kind of a thin ring and it is being experiencing some loading which is uniform in all directions, how that will lead to stresses developing within the material, and what effect will it have on the extension of the material, because this is very commonly used in many real world applications such as in tubes, any kind of tube through which you have some fluid flowing at a pressure, or the way that it has been shown in this in particular wheel where it is experiencing stresses which are not exactly hoop stress, but still they are stress being experienced by the rim of the wheel. But in tubes, any kind of pressure tube or for transport of any fluid, you experience this situation. So
Hello, sir.
I'll uh,
Sir, can you explain the for force deformation relation, sir?
force and
Can you allow me,
deformation
sir?
relation.
Can you evaluate, sir?
Okay, sure. So I think when we were discussing about linear elasticity, we looked at uh, if we consider the material as a spring for small deformations, we had this kind of expression which relates the force to the amount of deformation. So you were able to understand what this expression means? Shanmugh? Shanmugha?
Yes, sir. Yes, sir.
Hmm. So, do you have, like, you want me to explain a bit more in detail how this comes up, this kind of a
Yes.
linear effect?
Yeah, not that, sir. In a ring subjected to internal pressure.
Okay.
Yeah.
What will be the extension due to the who due to the pressure
Yes, sir, not
on
in
the
this
ring?
topic, sir. Ring subjected to internal pressure, sir.
Okay, I get it. So the topic which was covered in the next slides, right?
Yes, sir.
This one.
Yes, sir.
Okay.
In that,
So,
in the
hmm,
above PPT, sir. In the above. Yes, sir. There the equation is delta Fy equal to delta Fp sin theta equal to P. So can you evaluate that equation?
okay. Um, we can do that. So if we try to make a free body diagram of one half of the ring, then you have some stresses which are being experienced by the ring material. Let's call it Ft. And also since you have fluid which is going through, which is having some pressure inside the tube, there will be a uniform pressure being experienced by the inner side of the tube. Let's say the pressure is P. So for this um, body that I have considered, we can say that the net force above is, let's call this Fp, due to the pressure experience, and the internal stress, the force due to internal stress is Ft. So we can say that Fp will be equal to 2 times Ft, and we want to know what is the expression of Fp. So for doing this, what we can do is we can take a small portion of this ring. Let's say it is at an angle theta. So let's say this is theta. You have this small portion. It makes up a angle d theta. And since the radius is considered as r, we can say that this length of the small infinitesimally small ring, portion of the ring, is r d theta. And because the pressure is not acting in the upward direction only, for different parts of the ring it is acting at different directions, we'll have to find the component of the force which is in the y direction, and then we'll have to integrate it for all the small portions of the ring in order to get the resultant force in the y direction. So here we know that the force experience will be equal to small p into the length of this ring, this portion, which is r d theta, into the breadth of this. So by breadth, I mean this portion B, which you can see here, because over this whole thickness, let's call it thickness. Um, we can maybe call it just the breadth. So over this whole breadth, we'll be experiencing the same force. So it will be P into R d theta into B. Let's say this is dFP equal to this, right? So, but the force which is being experienced in the y direction is going to be dFP sine theta, right? And if we want to integrate this whole thing, since we want the force, so this is the force which is experienced in this small portion in the y direction, right? TFP was experienced in this direction, and we took sine theta so that we get the uh, force in the component of the force in the y direction. So if we now integrate this from 0 to, let's say, 180 degrees, since we are looking at half of this ring, okay, okay, then this will be equal to, okay, so there is some issue with my pen. I'll quickly try to see what is the problem. Yeah. Okay, so let's continue. We were doing integration from 0 degrees to 180 degrees. So this will be equal to P into small r into B into sine theta d theta from 0 to 180 degrees. And this will be equal to PRB into integration of sine theta will be minus of cos theta from 0 to 180 degrees. And this will be equal to PRB into 1 plus 1. If you do the calculations yourself, you can see why it will be equal to 1 plus 1, and it will be equal to P into small 2 into P into R into B. And we know that if the net force is 0, then you have this expression Fp equal to 2 times Ft. So from this, we can say that Ft is equal to small p into R into B. So what we basically did was we broke it into small portions, the ring into small portions, because every portion of the ring is experiencing force in a different direction. So you can't directly add them up. You have to take components of every small portion and then add them together by integrating. And you'll get this expression Ft equal to small p into R into B. And now if we look at how we can use this, then we can, if we know the Young's modulus, so I have not explained Young's modulus, right? But you understood that previous part. If you have any questions, you can let me know.
No doubt, sir.
Okay. Okay. So let's continue. If you know the value of Ft, which is the force experience internally in the ring, then you can try to write down the value of the elongation being experienced by the ring if you know the value of Young's modulus. So Young's modulus is nothing but a elastic constant, which tells you what is the stiff. It will tells you some give you an idea of the stiffness of the material, and it is defined as follow: E is equal to stress by strain, and for a particular material, it will be constant. Assuming that the material is isotropic, it will be constant. So E is equal to F by A divided by del, if del is the extension, divided by capital N, the initial length. And by
Yes, sir. I
using
have
this,
a good idea, sir. PL by AE.
yeah, so by using this expression for E and the previously obtained expression for force, you can get the value of elongation of the ring as well as the elongation of the radii of the ring due to the pressure in the tube. We'll also be doing a problem on this today. So there also you'll get some clarity.
I have a small doubt. So the length became 2 pi of r plus t by 2.
Yes. How it became like that? Okay. So the reason we are writing it as 2 pi into small r plus t by 2. So here 2 pi into r plus t by 2 is actually the total length of the ring. And because if you have this kind of ring, I'll just, you know, if you have this ring, so probably in the lecture this might have been discussed, but I'll again just touch upon what is being done there. So if you have something like this, then you can see that the length of the inner portion of the ring and the outer portion will be different, right? For the inner portion, it will be 2 pi into smaller. For the outer one, it will be 2 pi into r plus t.
Yes,
But
sir, but it is given as 2 pi of r plus t by
e-
2.
yes, I get it. Yeah. So if you cut it into half and if you straighten this out, you'll see that actually the length is something like this. In the sorry, since the inner portion and the outer portion are having a different length, it will not be totally rectangular shape. But in order to simplify it, because we need to simplify it in order to use our mathematical understanding to develop the mathematical relation, we are assuming that it has an average length of 2 pi into r plus t by 2. So it's an assumption. And based on that assumption, so basically what we are doing, we are saying that we can straighten it up and say that we have a kind of a plank of this length 2 pi into r plus t by 2, and this plank which is something like this is experiencing forces ft, and now we are using the Young's modulus and the linear elasticity relation to understand what will be the strain extension that will develop in this particular plank. So we are simplifying the problem by assuming that you have a constant length of this value. Is it fine?
Yes, sir. So any specific reasons for taking thickness as t by 2 other than because here the thickness is very negligible, so we are neglecting it. But if the thickness is little bit more, we cannot neglect because it is more less than 1.
Yeah. So depending on your particular case, if the value of t is comparable to small r, then it will not be advisable to neglect the thickness value. So there you should not be neglecting it. But here we are assuming that it's a very thin ring. So in the final expression, sir has neglected the t portion of it. So in engineering problems, it is always case dependent. What assumptions you should be using. Many a times, a few assumptions will not. It will not be as advisable to use a few assumptions, which you might be using in generally for other things. So uh, if this is clear, we will move on. Or if there are questions, you can ask in between.
Sir, can you show me the divided by The equation derived by you, sir. I will have a quick screenshot.
Derivation of this expression for this slide.
Yes, sir. Did by you, sir. You did it, no, sir. I will have a quick catch up. I will have a quick.
Okay, you mean this derivation?
Yeah, yes, sir. Yes, sir. Just a second, sir.
Okay. So a recording of all these sessions will be uploaded on YouTube. So in case you have some doubts or want to go back to something that was discussed, you can always use those video recordings. But of
Yes,
course,
sir.
it's much better to join the session live so that you can interact and ask right whenever you have the doubt.
Sir, one
Okay.
more doubt I am
Thank you, sir.
the orthotropic part.
The orthotropic part where it
I
explains
couldn't
the
understand the example.
for the wood you mean.
Anisotropic and
Okay, I think sir had mentioned that in certain materials like wood are not isotropic. They have a particular kind of an isotropy called orthotropy. So you want to know more about it, and I'll have to see where it is.
why we are calling it as orthotropic?
Why we are calling it as orthotropy. Okay. I'll quickly try to go to that slide if it is possible. Or we can go to it. I'll just explain you directly. So firstly, try to just understand what is isotropy and anisotropy. If you have a certain material, for example, if you have this kind of a material and you are loading in firstly in one case in this direction and in the other case in this direction, if the properties that you are observing, for example, let's for simplicity just consider the Young's modulus. If E1 is equal to E2 for any kind of loading, doesn't matter which direction you load it in, then you can say that the material is displaying the same property irrespective of how you are loading it or which direction you are loading it in. So there you will say that it is isotropic. But in case the material is not is showing directional property, so if E1 is not equal to E2, then you say that it is anisotropic. But many a times material is not totally anisotropic. So it might happen that for let's say E1 and E2, there is a certain relationship between E1 and E2. Not the same, but due to the symmetries that are present in the material, there are certain relationships. For example, in wood, they explained that you can assume it to be different layers having fibers oriented in different directions, and all these different layers are stacked over each other. So something like this. Here the orientation may be different. And similarly, another layer having a different orientation. Because the wood that you have, it has this kind of fibers in it. So this is also a simplification, but it has some fibers of this kind, right? You see ring. And since you are just using a rectangular cross section of it, something like this, you can assume that on an average the material will behave like a superimposition of all of these different layers having fibers oriented in different directions. And this particular thing is called orthotropic, or it's called an orthotropic material. Exactly what are the details of the symmetry that you observe for this material, you'll have to look up in more detail. But for now, uh, for our context, I think this much should be enough. Uh, I hope you could understand to some extent. If you have any questions, you can let me know.
Yes, sir. Clear.
It's clear. Okay. So let's move ahead. So we talked about the stress experienced in a ring, and thickness will also have an effect. So you can see it here that different at different radii, the stresses are have a circular symmetry, but at different radii, the value of the stresses are different. Now let's move to stress vectors. So I think this will be the last lecture I'll cover, or I'll try to cover fifth lecture if we have time. Till now, we looked at the stresses for in case of a uniaxial tensile test. But if you have a material which has some small holes in between, even though the portion of the material which is being removed in these holes is very small, the stress state is that is developed near those hollow portions is not uniform at all. It will be very concentrated. So just near these holes, you will have very high stress concentration region, and as you go away from it, it will become more uniform. But this is how most of the components we use are actually, because we need to use holes for inner components so that we can apply loads to them, right? We cannot join material directly so easily. So if you have these kinds of components, you'll have some high concentration stresses near those load application area. And we would like to know how those stresses, how much the stress values are, so that we can estimate where we can estimate till what load we can use that component and when it might fail. So this is a link which is used for making change, for example, in cycles or motorcycles. And here also you have a similar kind of geometry having a hole in it, and you apply load on these links near the hole. So now let's move to understanding how we can mathematically represent the stress state in any point in a material, so that we can better work with the stress values which the material will be experiencing. For this purpose, let's assume we have this kind of a body and there's a point on it where we want to know the stress state. So we have cut it at a particular uh, on a particular plane, and the stress vector, that is the force vector which is experienced at that point for if you cut it in this plane, let's say it is delta t, and you are considering the force experience for a infinitesimally small area delta a. So the stress vector for at this point will be equal to delta t, the force vector for this small region, divided by delta a, which is also very small, and you take the limit tending to 0, and the stress vector which you get as a result is represented like this t, and we also call this as traction. Here n is the normal vector to the plane. All of this has been explained in a lot of detail in the video lecture, so I'll suggest that you first go through those video lectures, or if you have doubts in this session, you again can go back there and try to understand it in a sequential manner in which the professor has explained it. Yeah, please, you can unmute and ask.
Yes, sir. So we are having something called NX, NY, and NZ, right? Are they planes or something like that? In the last equation of the tensor.
Okay, so can you repeat one, nx and ny? Mhm.
Yeah, in the last equation of a tensor, we'll be having a matrix of nx, ny, and nz.
Right, right.
Are they
Hmm.
planes or something else?
So here, right?
Yeah.
Okay. So what I'll do, this is part of lecture 4 only. I'll cover till lecture 4, and at the end I'll explain that also. First, let me just give a brief uh, understanding of the initial steps to it. Slowly we'll build up to the tensor form. So here we have understood what is the stress vector for a particular point in the material, which is cut at a particular plane, and the normal for that plane is represented by n, this n vector. And there can be infinite number of planes which will pass through this point. So you can have infinite number of stress vectors for a particular point. And if you have a particular plane and a point, then the stress vector can be resolved into a normal stress component and a shear stress component, which will be something like this. Yeah. So you can resolve it into normal and shear stress component, and also you can resolve it into the components along x, y, and z direction given by tx, ty, and tz. Also, the shear stresses can further be resolved as along tau xy and tau xz. So the for understanding the notations, what x, y, and xz mean, you can refer to the lecture. In brief, for this scenario, I'll tell you that here we are considering the plane x. For xy, we are considering x to be the plane on which the force is acting, and y is the direction in it. So the plane is the one perpendicular to x direction, and the direction of force is in the y direction. So we call it tau xy. And we can similarly have tau xz, which is the component of shear stress along z. And then you have sigma xs. So this tells you about the stresses being experienced at this point for this particular plane, which is the x plane. Okay. Similarly, you can do it for the y plane and the z plane. Also, sir mentions in his lecture that you can have an infinite number of planes which pass through that point. But to know the stress state for that particular point, it's not necessary to know about the stress vectors for all those infinite planes. Just knowing it for three orthogonal planes is enough for knowing the stress state. So these orthogonal planes can be the x plane, y plane, and the z plane. And pictorially, the stress state can be represented in this fashion. So there are certain conventions that are used. So normal stresses in the x direction will be given by sigma xx. The shear stresses on the x plane will be tau xy and tau xz. Then there will be some conventions for the signs of these stress components. We call all of these stress components. So in the negative direction, we'll have a negative sign. So I won't go into those conventions right now. But if you have doubts, you can look at the lecture or you can ask me if you have particular doubt. I don't want to rush through all of these, but if tomorrow also these Archita will be covering the stress vectors and maybe on stress tensors also. So you can again Ask her also if you have any particular doubt. So now that we have a particular convention of representing the signs as well as the stress component for the shear and normal stresses, we can for any plane write it in this manner. And then the stress vector in the x direction, y direction, and z direction can be written as in the by using the normal stresses and the shear stress value. And since you are doing it for a particular plane which is represented by n cap, the normal vector to that is n cap, and it will also have components in the x, y, and z direction. So let's say those components are nx, ny, and nz. So I think the question asked was related to this. So if you have this kind of, let's say, force Tx, stress vector Tx, and sigma xx acting on this plane in the xx direction, in the x direction, this is the normal stress. Then it will act on an area which will be equal to A cross Nx, because this area is inclined. This plane is not parallel to the x-axis. The normal to this plane is not parallel to the x-axis. It is inclined. It will have a component Nx, which will in the x direction. So sigma xx will have to be multiplied by the area which is being experienced uh, in the x direction. So let's say the component of the area in the x direction will be A into Nx. I hope I was clear. So because of that, the value of Nx will be important for knowing what will be the contribution of sigma xx to the stress vector value in the x direction. If you have doubts, you can ask me.
Can I understand that the NX is an inclination angle of that plane?
Yes. So let me just draw it to make it more clear. So if you have this plane, let's say it is like this. You have the x. Let's say this is x, this is y, and this is z axis. Then the plane here, if this is the n vector, let's say it is n cap, then nx will be nothing but equal to n cap dot I cap, where I cap is the unit vector in the x direction, and this will be equal to cos of theta with the x axis. So theta is the angle of this plane's normal with the x axis. So nx will be nothing but the value of cos of theta. You are taking a component of the normal with the x axis.
This NX in our term is sigma axis.
Can you repeat one?
The NX in this area is what we are telling it as sigma axis in derivation.
Yes. So this nx that I have written here, this is what is being used in that derivation also. So write the stress vector in x direction Tx as a function of sigma xx, tau yx, and tau zx. So for every plane passing through this point, there will be a particular normal vector, and it can be written in terms of the components nx, ny, and nz, and that you can use to calculate the value of Tx for that particular plane. Because sigma xx, sigma yx, sigma zx will be constant for that point for a particular reference system. So x, y, and z axis are constant, and these components are also constant. But depending on what the plane is which you have chosen, your Tx will be changing. If in case you have doubts, you can ask me. If this is clear, then the other uh, stress vector values such as Ty, Tz will also be similar. So you can understand this as every point having a stress vector T, let's say Tn, for a particular plane, and this will can be written as a function of the value of stress components which are invariant of the plane you have chosen. It will only depend on the coordinate system that you choose, and we want to represent it mathematically. So if you do the force balance for x, y, and z direction, we saw how it was for Tx. I didn't show the force balance exactly. I'll ask Karchita to spend more time on this and directly start with this part only, so that tomorrow when you listen to her session, you'll get a more in-depth understanding of this portion of how the force balance was done and how we obtained this expression. But I'll just today gloss over these things so that we can spend the next half an hour on the problem assignment question. So you can get this kind of an expression for Tx, Ty, and Tv, and then it can be written in a matrix form where you call this as a stress tensor, and you multiply it with this normal vector for your plane, and you obtain the stress vector. In the next lecture, the next lecture is more about the stress tensor that you have obtained here, made of these components. But I'll stop here for now. If you have any questions you want to ask related to this now, you can ask me.
No, sir. Thank you, sir.
Okay.
This one
So
is
we'll
easy.
you are able to understand it to some extent.
Yes, sir. Actually, I did a course on means I understand tensor and even stress tensor, the relationship between stress and strain tensors.
Okay, I see. If you have some mechanical background, this might be easier to grasp.
Yeah, actually, sir, I am an aerospace engineer.
I see. Okay. Then you might be knowing.
Yes, sir.
Okay, so I'll now move to the problem assignment where we have a few questions related to these concepts. We'll try to look at them. Since we have a good number of participants, I'll request you all to just read the question and try to answer it yourself. You can maybe write the answer, just write the correct option in chat. Then we can discuss what the answer should be. Just go through the question and spend 2 to 3 minutes.
Sir, the timeline for submission of assignment has passed, right?
Um, the timeline for submission of assignment, I'll have to check it. I am not aware.
Okay, just
On
give
the
me a moment.
NPTEL portal, you might be able to see. Is it has it passed?
Just a moment, sir.
The rest of the participants can try to answer.
Yes, sir. 5th was the due date.
Uh,
Oh,
5th February.
yeah, 5th Feb is the due date, sir. It's still time is
Okay.
there.
So you still have.
So if we discuss the answer, sir, then it will be I have completed the assignment.
Yes, so you will, those who have not worked on it, they can also uh, discuss it
Yeah.
in these sessions. But I think the purpose of the assignment is so that you spend some time on those concepts. So you can try by yourself first and then also discuss it when Archita is explaining in the next session.
Yes, sir.
So try to do it yourself by today if possible, because then only you will also generate doubts. Unless you try to work on problems, you will not know what are the gaps in your understanding. So my suggestion will be go through your lectures religiously, look at the assignments in between, and try to see if you are able to answer the questions well. And then you should come to these sessions. That way you will be able to utilize it well. So were you able to solve this first question? You can let me know what the answer should be.
Sir, no doubt. Sir, will we be discussing regarding the tutorial problem which sir gave in between, I think, sir lecture?
On the pipe pressure,
Ah,
the
yes, yes,
tube
yes.
one,
With
no? Yeah,
stainless
yeah,
steel.
it's we'll discuss on that. Yes. In the subsequent question, it will be there. So there we'll be discussing on it. Hmm. If any of you know the answer to this, you can quickly write in chat.
Chat is disabled.
Krishnakant, you know the answer.
Sir, chat is disabled.
Sorry, I could not understand. What did you say?
So chat is disabled, so we cannot send messages in chat.
Okay, right now you can't send messages. Okay. Okay, so just tell me on through your mic only. I'll try to change the
Yes, sir.
setting for chat.
Option B.
Option B. Option B, you said.
Yes.
Yeah, B is the correct answer. So, rigid body does not have any deformation. And the reason it does not have any deformation is because we assume that the constituent particles do not change with respect their position with respect to each other when an external force is being applied. It's like a frozen material which will not move. So let's go to the next question. See if you can answer this.
Sir, I had a doubt.
Yes, you can.
Sir, before our the certification exam,
Hmm.
will we be some kind of this practice session for the exam? Will we do that also?
Practice session for the exam.
Yeah.
Right now we have not planned anything. So the plan is that we'll for every week session in these doubt solving sessions, we'll have some questions like the ones I've been asking right now. So these will help you to engage with the week content, but we have not planned any particular session for the exam. We can keep a
Okay.
doubt session for the exams where if you have solved any problems which are from out of this code or which were from some other reference book, you can ask from there also. But we'll restrict ourselves to these problem questions.
Okay, sir. Thank you,
But
sir.
if you have any questions related which are from some books which you have gone through, you can post it maybe in the chat here, or we can maybe make a small group where you can post it if you require it.
That will
I
be
think
great, sir. Actually, it will be very helpful.
NPTEL has a Google group where students ask questions. Last time I had seen that. So you'll be having that Google group. I'll just
Okay.
look at what the link to that is. So I'll let you know in tomorrow's session.
Sure,
So
sir.
there you can ask your questions, or if you have any suggestions, you can make it. Okay. Now I have changed the settings. You might be able to write in that. So who can quickly answer what will be the correct option?
It might be C, but chat settings is not yet open.
Not yet open. Okay. Yes, it's not open. Okay. Since we have less time, we'll just look at the other question. Chat I'll look at later. The correct option will be C.
C.
Stress is a measure of the internal forces which are being experienced in the material. And these
Yes.
internal forces are present because the material is trying to resist deformation, which is due to load which is being applied externally. The correct option is C. Let's go to the next question. So, can someone answer this?
B, sir.
B. Okay,
B.
both. Yes, the
Yeah.
correct answer is B. So, when you are dealing with engineering problems, you have to make some idealization or
I have one
assumption.
doubt regarding this, apart from
Yeah.
this. So, how we have to understand, we have to make idealizations like this. So, how we are getting those kind of stuff? How
Okay.
to know
How?
we can make assumption on this, and we should not make this assumption like that.
Okay, I see. So, many a time, um, many a time, the problem that you're looking at is so complex that you'll have to only restrict yourself to the major forces or major parameters that are at play. So, what we always try to do is to break down the problems. For example, here what we have done is we have assumed our material to be in the elastic regime, isotropic. So, we make this assumption such that we can work on the problem further, but we also need to be aware that these assumptions will cause us to get results which might not actually be true, or they might be very much away from your what you'll get experimentally. So this has to be done on a case to case basis usually, but here we are trying to get a mathematical understanding of the stresses in a material. So we'll make much more bigger assumptions, and this is a very general assumption that we are making. When looking at particular problems in real life, you'll have to uh, not use many of the assumptions. You'll have to bring up more parameters so that it will mimic what is happening in real life. I hope you could understand a bit.
Yes.
So this is in a case to case basis, whether assumption will work well or not. But there will always be some assumptions you will be making. So for example, for the bridge case we saw, you know that there will be some forces acting, that the material has certain property in a certain direction. So those things you know, but there will be also many forces which you will be neglecting. or which you will not be able to quantify. For example, the effect of different kinds of vehicles on the bridge or different weather conditions on the bridge. So that will also have an effect. Corrosion will have an effect, but you cannot directly quantify that when you are trying to design that bridge, right? So there you will say that you have done made an assumption that there is nothing else acting on that bridge. So it's an idealization, right? So in that sense, you will have to do it. If that was clear, we'll move ahead. So the correct answer to this is B. The both statements are correct, and the reasoning is also correct for the question. Coming to the next problem, you can take a look at it.
Isotropic
Isotropic.
and homogeneous.
So all of you have the same answer, isotropic and homogeneous.
Sir, actually, I have a small confusion. Sir, isotropic means laying fibers in same manner, right?
Isotropic,
Laying
can you
fibers
repeat
in
me?
same.
In same manner. Okay. So your question is, does isotropic mean laying fibers in the same manner?
Uh,
Okay. So when we are saying isotropic, it's a more general property. So when you are
The
saying
forces.
fibers, uh,
Sorry, you continue, sir.
yeah. So I was saying isotropy or anisotropy is a more general property for any material. So one case it could be that the material is a fiber reinforced composite where you have fibers which are very strong in a matrix. So there you will have directional properties as I told a few minutes ago when I was talking about isotropy. So there you have directional properties and it will always be some kind of an anisotropy. But isotropy is the most ideal condition where in every direction the material will behave exactly the same. Usually that happens when you have a material, for example, in case of metal, if you have a metal which has been heat treated for a long time, so that the microstructure of it is very uniform. All the grains are similar, similar in morphology. Then no matter how you, in which direction you apply the force, the value of the property you get will be the same. So then you call it that it is close to isotropy.
Sir, can we have isotropic nature for a heterogeneous material?
For a
Like
heterogeneous material.
mixing two or more material and laying it in the same manner, like that can we have?
Yeah, okay. I get your question. Yeah. This is a good question that you have asked. Whether if your material is not homogeneous, so we have understood that we are assuming homogeneous property or the material to be homogeneous as well as isotropic, but these two are not exactly the same. So it could be that you have a heterogeneous material as was asked by the previous speaker. So you might be having uh, different atoms or different components in that same material. For example, let's say you have a metal. Since my work is more involved in metals, I can maybe give you an example related to that. You have a metal and you look at it at high resolution, you see that you have particles which are embedded in it, which is very common. Let's say these are some oxide particles or some reinforcement particles. So let's say this is a particle reinforced composite having a metal matrix. Then this is not a homogeneous material. Right? You have two different components. You have this hard, let's say a ceramic particle, and this much more tougher metal matrix, and this is heterogeneous. But if you look at the isotropy, this is very randomly dispersed. Let's say the particles are randomly dispersed. So in every direction, the interparticle distance will be the same. So the properties that you measure will also be the same in all directions. So this is isotropic, but this is not homogeneous. So it's not necessary that every heterogeneous material will have to be anisotropic. It can also be isotropic. But generally, I think I couldn't make a blanket statement. But if you have a anisotropic material, it's likely that it will be heterogeneous. Okay, so let's look at the answer to this question. So the correct answer will not be D, it will be C, homogeneous only. Since we are only talking about properties at single points and not in different directions, the correct answer will be C,
Yes, sir.
homogeneous. Okay, so now let's look at the next question.
Can we select two?
D.
You can select multiple options for this.
Then B and D.
B and D. Do you require more time or should I discuss this?
Explain, sir. B. I said D.
Mhm. Okay,
I
the
think little.
correct answer is B. It's B, and so this is the correct option. Then I
And
think this also will be correct, and you also have. So you said B and D, na? But this is F. So all three will be correct. So you cannot know the values of the forces uh, acting at all points for all of these three cases. So let me briefly explain how you can understand this. Here we have um, these three, let's say these three different scenarios. And let's say you have this scenario here where you only have, uh, let's say, a wall here at one end of this cantilever. So here, if you try to see, if you make a free body diagram, so this is a general case where we know that we can know the forces. So if P is being applied here, then at this wall, you will have um a movement being applied so that it can resist the deformation, resist this shock due to the force which is being applied on this bar. So you will have a movement M, and you can write M as equal to P times capital M, the distance at which it is being applied. And you can also know, let's say that this is the free body diagram. Here I also put the one. So if this is P, then there will be some force in the opposite direction which will also be equal to P at this wall, which is the internal resistance being offered by the wall. So you will also have P here, and it will be same in value as you applied for, and you will have this movement also. Right? So you can know what are the values of all these forces. But if you have two different walls of these kind, then you have more number of variables and less number of equations. Constraints are more. So you can have a movement being applied in this direction M1, in this direction M2. You can have a force, a shear force here P1, and here you can have P2. So you have four different variables and just two equations. One is the moment balance and one is the force balance. So here you cannot find all the values of the forces. So this will be one correct option. Similarly, in this case, you have forces being applied at three different locations. So if you want to do a force balance, you will have three variables in this one equation. So here also you cannot tell what will be the value. So you will also have a movement equation. So you will have two equations, but three variables. While in this case, you will have you only have two contact points, right? For the C case. So for these two contact points, you will have some forces and you have two equations and two variables, so you can solve it. Similarly, in this case, you have three variables, the movement being experienced at the wall, then the forces experienced in the y direction at the two contact points. So here also you will not be able to get all three values. So these three are the correct options. If you
Sir,
have
what
any
is
doubts,
the
you can let
beam
me know.
called?
Sorry,
What is the last type of the beam? Continuous or fixed?
the last type, this one,
Yes.
whether it is continuous or fixed is your question.
Yes.
No, I actually couldn't get what you are asking. So you mean fixed at one end?
Yes. Yes. Yes.
So here, this is what this means is if you have this kind of arrangement, this is a wall which so one end of your bar is fixed at the wall, and the second end is in contact with this kind of thing. And here you have small bearings, so this can move in the x direction, but it can't move in the y direction. So the bar, this contact point with this portion can also move in the x direction. But here, since we are only applying force in your y direction, we are not concerned with this thing. So this is how the arrangement is. So it is only constrained in one direction. If you look at x, for y it is constrained in both directions. Sorry, not in both directions. At both points it's constrained for y, and for x it is only constrained at the wall, which is this one. I hope it was clear. So let's do two more questions and finish for the session. Archita can take up this question because it will take much longer. The question related to the elongation of the ring due to internal pressure and the effect on the change in radii due to that. So this will be taken by Archita at the start of tomorrow's session. And we'll quickly do two numericals. Okay, this is just a multiple choice question. Go through this in the next 15 minutes. If any of you knows the answer, you can let me know.
One is a confirm answer, sir. It's stress concentration zones. I'm not sure about others.
Okay, there will be multiple answers.
Okay, 2 points. So, when no hole is present in the specimen
Sir,
for the
last
given.
internal resistance section B due to applied load.
Just tell the option number that you think is correct.
A
And I think E is correct for
is
One and
B. The
last,
portion internal
right,
resistance
1 and 5.
is uniform at section B due to applied load P.
Okay, five options.
Yeah,
So you are saying E can be correct option and A can be correct, right?
and A.
A is correct. A and
Okay,
C, I guess. A is correct though.
so A will be correct. Since as I said, the fringes tell you about the stress values, and more fringes near hole means that then here the concentration of the fringes is higher, and that means stress concentration is happening. And far away, okay. Also, E will be correct because far away from the hole, the stresses become almost uniform. And if C will not be correct, because if the stresses are uniform, then you should not be seeing variation in the color. The color will be uniform totally.
Yeah. B will have uniform section. A cannot be uniform.
Okay, but C will be correct actually. If you read it carefully, it talks about how the stresses will be far away from the loading lens when no hole is present.
But sir, when we are twisting, when we are applying moment only, we will be getting high stresses at the ends.
Sorry, when you are applying movement.
When we are applying moment only, we will be getting high stresses at the end.
Hmm.
Yeah.
If
Um,
pattern top at the maximum center.
But C, point C is talking about uniform color appearance.
yes.
Appears in the regions far away from the loading ends.
But for even for the loading regions, it has not mentioned any region A or B. So for those cases, uh, there will be fringes formation, and because the center loading there will be zero stress. So far means on the longitudinal side only we'll see the fringes. And that is my explanation to it.
Uh, okay. So if we look at C, which talks about when no hole is present in the specimen, that means that you have a uniform bar, right? And there
Yes.
you are applying this kind of a uniaxial load. So in the x direction you are loading it. So here you expect that the stresses will be the same all through the material, right?
Yes, sir.
Since there is no region where there should be stress concentration happening. So there you expect that the color will also not change since the stress values are not changing. So here, even if you are far away from the loading end, that is in this region, this is farther from the loading end, right? The A region. So here also you will have a uniform color. That is what is being uh, told in the option C. So that's why C will be correct. In case you have a hole, then you will have stress concentration which will be present away from the loading regions, which is A. So then you'll be having. But if it's not there, then it's uniform. So C should be correct. If you have any doubts, you can ask. And someone was asking related to bending, that in case of bending you will have stresses near the
Yes,
loading end,
but
right?
what I thought is they are speaking about a faraway region from the loading edge. I thought it is a topmost and bottommost region.
Okay, I see. Because it's being loaded locally as per this picture, right?
Yes.
But here we are assuming that the load is actually being applied on the whole surface. Else again we'll have stress concentration near this part. This is just for
Yeah.
representation, but we are assuming that stress is being applied on the whole surface.
Yes. So if possible, can I ask some informal doubts?
Sure, but
Sir,
I think we
regarding,
have
I'm basically a research enthusiast, completed BE Arrow.
okay. So what's your name? Can you just
Yes, sir. So,
Krishnakant?
sir, actually, as a PhD scholar, what you will be doing, sir, reading many books regarding your subjects, or reading only to your thesis, or both you will be doing any specific stuff, because I am interested in research, so it will be very helpful in my future.
Krishnakant, since we have a bigger audience here and time is also up, everyone might be wanting to go. So you can
Okay.
connect with me by on mail. I'll be happy to help you guide you depending on what your
Sir,
situation is.
can I connect with you through?
Firstly, you can just connect with me on mail, then we can see. You can just send a small mail to me. You have my mail ID, right?
Mail?
I'll write it in the chat, and then maybe I can help you with your specific question. We have one more question that we'll discuss here, then we'll close. It's already 8 p.m. I hope you can see my chat.
Sir, so what all options were correct? A, C, and D, E.
A, C, and E were correct, right? We didn't discuss the E option, right? So E option is that internal resistance is uniform at section B due to applied load P. B is far away from the hole, so there it will
Yeah.
be more uniform. So there
Yes,
was
sir.
an effect. Actually, this was explained in Sir's lecture. So he had told about effect. I'll just go through that part in the tutorial quickly. Anyone who knows that the name of that effect, which tells of that phenomena, which tells you how the stresses will change as you move away from your stress concentration side. If you know,
I
you
don't.
can just tell me. Those who might have paid attention to the whole of the lecture, they might be knowing. So there you can read in a bit more detail how the stresses change as you move away from your stress concentration side. Yeah, I'll have to search for it. I can't see it right now here. But the essence of it is that as you move away from your point of stress concentration, so for example, if you have this kind of a loading, and this is a very important assumption that we make when we try to understand the stresses in any engineering component, that if you have this kind of a hole, then of course you note that you have very strong stress concentration. Um, Here it will be at these points, right? So you have very high stress concentration. But as you move away, the contours will become more uniform. And this assumption is very useful because in most engineering applications, you have some particular uh, places where you are applying your load, for example, like this, and you will always have some stress concentration side, because even if you, for example, have trusses, you have some rivets which are present, which are used to join the trusses, and these are the points of loading. So here you will have the maximum stress being experienced. But for looking at from a design point of view, you will just assume that uniform stress is being experienced by this stress all over the cross section. And why you can make this assumption is because as you move away from your point of loading, it actually becomes uniform. So in most cases, it is fine to make this kind of an assumption. Now let's move to the last question and finish it. This is a numerical question. What I'll suggest is you look at it and try to answer it yourself. Since we have exceeded the time,
Sure,
you
sir.
try
Can
to
you zoom a little bit?
just take a picture of it
Yes, sir.
and solve it yourself. If you have doubts, you can then ask me in the Google groups that we'll be creating, or NPTEL might have already created it. I'll share the link with you all.
Sir, the group is not there in the course.
For this course, you don't have Google group.
No, sir.
Okay.
I think I saw a group on my emails for the course, a link to a group.
Yeah, there it came. Yes, let me check.
Mhm.
Sir,
So
I
you all
request you to
can.
please zoom into the question.
Yeah. So you can look at the groups later. I'll also take a look. Just take a picture of this question. If you have doubts, we can just quickly discuss the answer to this in your next week Friday session. Okay, you have taken a picture. This is the answer to it. So your answer should be within this range.
Sir, can you go back to question? I couldn't take picture.
Okay.
Thank you, sir.
Okay. So if you've taken a picture, just take a picture of the answer also. What I'll do in the next Friday session, I'll quickly solve this question, and then we'll move on with the week content.
Okay, sir.
Okay. So let's end this session with this question. I hope that this was useful for you. Since this was the first session, there might have been some hiccups here and there, but we'll try to answer the questions that were asked today in tomorrow's lecture, and slowly we'll try to make this more efficient so that it will be helpful for you all. If you have any more suggestions, you can let me know either on mail or in the next session you can let me know. So I'll suggest that you all attend tomorrow's lecture where more focus will be on discussion on the assignments and that problem which was for that pressure tube, right? So thank you all for attending. We'll close
Thank you, sir.
now. And
Thanks,
I
sir.
hope that
Thank you. Thank you. Thank you.
I really hope that these interactive sessions will continue with the same energy or more energy in the subsequent sessions. This was more of a introductory session since we are looking at some basic concepts, but later on it will become more complex. So there I hope that you will keep interacting this way, and we'll also try to cater in the best way possible. So thank you all for attending.
Thank you,
Goodbye.
sir. Sir, I checked,
Thank
sir. There
you.
is no group actually, no link for any group.
Okay, I'll look into it and then let you know.
Sure,
So
sir.
we'll arrange something. Thank you.
Yeah, thank you, sir.